We said at the outset that reaction rates depend very strongly on temperature. And so now it's time to look at why that is and how that actually behaves. So if we increase the temperature, the reaction should get faster. That seems intuitively what you would expect, and it's definitely what we observe. Okay. Rate laws have a form that says the rate is equal to a rate constant K times concentrations raised to powers. We know that the powers, the X in the equation that I wrote there, have to do with the reaction mechanism, right? And so that presumably doesn't depend on the temperature. The concentration in general should not change wildly with the temperature. So that sort of thing suggests that the temperature dependence has to be embedded in the rate constant. Okay. The fact that we said in the beginning that K, the rate constant, is a function of temperature, right? So I can say it's K as a function of temperature, and that temperature dependence in there is what makes the rate change with temperature. So if we want to study this, we know a way to do it, right? We know how to measure the rate constant, right? We've looked at a couple of different ways we can get values for rate constants. So if we measure the rate constant at different temperatures, that'll show us what's going to be happening there. So this is basically the summary of this video. Okay, we're going to look at something known as the Arrhenius equation. That equation is in a couple of different forms over here, right? This one is solved for K. This one is in a logarithm form. All right. In that equation, there's A, which is just a parameter for a given reaction. Okay. Both A and E sub A change from one reaction to another. A is usually just referred to as a pre-exponential factor because in this version here, it's, well, the thing in front of the exponential, right? And so that A parameter we generally assume is at least roughly independent of temperature. Okay, for our purposes in this course, we're going to say it's definitely independent of temperature. A more careful development of the equation would say it can have a small temperature dependence in it, but that makes the equation much more complicated to work with. Doesn't change the actual end results very much. E sub A is what's known as an activation energy. We'll talk about that quite a bit in the video today. R over there is actually the gas constant, the same gas constant that you used in gas law equations, except that it's going to be generally in different units here. In working in this equation, this is usually going to be put in so that it's 8.314, and that version has units of joules per Kelvin per mole. All right, that's not it is the same number, just expressed in different units. So if you figured out a conversion to get from liter atmospheres to joules, you could do the old 0.082 number that we use a lot in gas law problems and get yourself to that 8.314 value, okay? The temperature in the equation, the T, that needs, like always, to be in Kelvin, right? Because we're multiplying, in this case, dividing by temperatures, have to be on an absolute scale. The graphic inset there says if we plot log of K versus 1 over T, it's a line, okay? And we can see that because this equation, the log version I wrote here, log of K is what's on the y-axis there, right? This piece, the minus E sub A over R, that's my slope times X, and this piece is B, the intercept, okay? So what does that tell me? That tells me the slope of this line is whatever is multiplying 1 over T in my equation. So that's the minus E sub A over R piece. Right, so if I had that graph, one way to get a value for E sub A would be to measure the slope of the line, then just do the algebra from there to solve that for E sub A. Right? The axis is 1 over T, so that means temperature. That means temperature is getting bigger this way, right? And so the rate constant, therefore the log of the rate constant, is going down as the temperature gets lower. That's what we expect. The reaction goes faster at high temperatures. High temperatures just happen to be over here on this end of the graph, right? Because the axis is 1 over T, so watch out for that. Right. If you tend to think about things graphically, if you remember that plot is a line with a slope equal to minus E sub A over R, you can use that often to solve for the activation energy. Alternatively, if we remember this equation here, then we can use that to solve for the activation energy by just doing some algebra. Compared to most of the algebra, I guess. Most of the arithmetic stuff that we do in this course, this equation will land you in some things that you have to be a bit careful getting out of them, okay? Just mainly because it's got that exponential term or log term in it. So you have to make sure that you remember how logarithms behave or how exponentials behave in order to make sure you solve correctly when we do that. So here's an example in which I will attempt to do all those things and make sure that I follow all the appropriate rules of handling those things. It says reaction is hydrogen plus iodine, H2 plus I2, making 2HI. It's first order in both reactants, it says there. We don't really need that for what I'm going to do here, but that's okay. We have values for the rate constant there at 2 different temperatures, okay? And so from those, we're going to find the activation energy. One way to do this, a relatively easy way, and a way that I actually might do this if I was doing this problem, would be to think about making that graph, right? I have 2 points, I have 2 temperatures, I have 2 rate constants, so I could make a 2-point version of the plot that was on the previous slide and do that. If you choose to do things that way, if graphing is a way that that works for you, then what we'd be thinking of is log of k versus 1 over t, right? And we're supposed to get something that looks like that. We only have 2 points, we're definitely going to get a line, and we could find the slope from that. So that's one way you could do this. That will lead to the same equation I should get to if I do all the math correctly here. So this says what? It says that I have my 2 rate constants up there. I'm going to actually put labels on them that I should have. I'm going to call that one K1, and I'm going to call that one K2, okay? That means this number here is what I'm going to call T1, and this one is what I'm going to call T2. I need that because I'm going to have 2 versions of my, my Arrhenius equation. My original equation said K, the rate constant, is equal to A e to the minus E sub A over RT. So I'm going to say I have K1 and T1, and I can write the parallel equation that says if I make it K2, it's A e to the minus EA over RT2. Between those 2 equations, the only things that are different are the ones with the 1s and 2s on them, okay? The activation energy and the pre-exponential factor, those are not going to change when I change the temperature, all right? R is a constant, it's not going to change. So the K's are different and the T's are different. Probably the easiest way to get started solving out of there, I guess, is to do something like, say, right now we have 2 things we don't know. We have A and E sub A in those equations that we don't know, right? We know both T's and both K's, and we know R. If I don't really care about A, the pre-exponential factor, so I'm going to divide those 2 equations by one another, okay? You can always divide equal things by equal things, and we should still have an equation then, an equality. When I do that, my A's go away, right, because I can cancel that. So now I have K1 over K2 is equal to E to the minus E sub A over RT1 over E to the minus E sub A over RT2. When you get to that point, there's good news and bad news. The good news is the only thing in that equation that we don't know right now is E sub A, the activation energy that we're trying to solve for, okay? So that means we should be able to solve for it. The bad news is it's in there in 2 places and they're both in exponents. And that means solving for it is a little bit of work, all right? Partly it's work because it's in the exponent. So the first thing to do is probably to get it out of the exponent. If I do that, I would get what? I would get log of K1 over K2 is equal to, and here's where you have to be careful, right? I'm going to leave that one as just log of K1 over K2 because K1 and K2 are going to be numbers eventually, so I can put them in there and just take the log of that. When I do take the log there, I have to take the log of the right-hand side, and I have to remember that the log of that, that quotient is the log of the top minus the log of the bottom, okay? And so that means that I get the log of the top is minus E sub A over RT1 minus the log of the bottom, which is minus E sub A over RT2. All right, so now I'm no longer up in exponents. It's getting at least somewhat simpler to solve from here. I can take that equation, and what I actually did is just to solve that equation for E sub A. All right. Students in general have a tendency to start putting numbers into things sooner than I usually do, but it should still work out if we do things correctly, right? And again, another option is to just think about that graph and do the equation for the minus E sub A over R being the slope. Effectively, the equation we've got over here, if we rearrange it a little bit, is the equation that tells us that's true. So let me just solve that for E sub A. And when I did that, I get E sub A, and I'm probably skipping some number of steps here that arguably I probably shouldn't, but I'm going to do it this way, is minus R ln K1 over K2 and all that is divided by 1 over T1 minus 1 over T2. If I put in the numbers for this now, I get minus, and R again is going to be 8.314. That's got units of joules per Kelvin mole. Really, I swear I'm writing letters. And then I've got the log of 2.45 times 10 to the minus 4. The units on these are going to cancel, so I'm not going to write them, right? Because both rate constants have the same units. I'm going to write this one as 0.95, I guess, since it's times 10 to the minus 1. So I can just do that and make it so I don't have to do another exponent there. Then down here, I've got 1 over T1. T1 is the 575. Minus 1 over T2, which is 781. Again, I have to be in Kelvin here. And when I do all that out, it tells me that I get 150,000 and my units are now in joules per mole because, oh, I didn't write them. That was bad. These, the two temperatures are in Kelvin. I said they were in Kelvin, but I didn't write the Ks. So let's do that. So the kelvins from the bottom and the Kelvin up here will cancel. So we would probably usually call that 150 kilojoules per mole. Okay. That's about the right general order of magnitude for an activation energy. So it's somewhat encouraging that we didn't do anything terrible. I didn't do anything terrible, I guess, since I'm the one who says that's the answer. It's really not liking writing here. Come on. All right, so you should typically for an activation energy get something that's between tens and maybe a couple hundred in kilojoules per mole, okay? Be very careful about units in here, particularly the gas constant part. All the time I see people stick in one of those other values, like the 0.082 number in particular, right? That'll make a big difference. If you were going in the other direction, if R is in joules, meaning that 8.314, if you know your E sub A and you're putting it in there, you have to make sure that the E sub A is also in joules then and not in kilojoules, right? Because if you put, you need to make sure the exponent ends up with no units, which it should as long as the energy units are the same, right? If E sub A is in joules per mole and R is in joules per mole Kelvin, multiply that by the Kelvin, then all the units go away. If you do put kilojoules for E sub A and joules for R up there, then you'll be off by a factor of e to the 1,000th power, which is actually quite a lot. And so be on the lookout for that. There are, as you can see, just look at that, a lot of ways to mess this up. And so it's good to be sort of just, make your way through it slowly. I actually like to do these problems one of two ways. One is like I did here by just starting from the original equation, the a e to the minus e sub a over rt part, because that's an equation I know and I'm not going to forget. I would never, for example, just try to remember this equation and write it down, because I know if I do that, if nothing else, I'll probably end up with the 1s and 2s crisscrossed in some weird way that makes my sign come out bad. Okay. The other way that I very often do these is just to think about the graph and the fact that log of k versus 1 over t is aligned with a slope of minus e sub a over r. And that's a good way to guide yourself to one of these. Again, that really effectively is an equation you can get to pretty easily from either this one up here or that one. You could just write the equation for the slope as like the change in log of k over the change in 1 over t, right? And that will give you the minus e sub a over r pretty well from here really easily. If you just remember that the log of k1 over k2 is log k1 minus log k2, then we're just about there. The other thing people do when I see people doing problems and messing them up here is just doing something bad, like when I took the logarithm of this term here. If you're not careful and you write down that it's minus e sub a over rt1 over minus e sub a over rt2, then you would have disappeared the e sub a, which is the thing you're trying to solve for. And that's not obviously good. It's also not true, right? Because the log of that is not equal to the log of the top over the log of the bottom. It's equal to the log of the top minus the log of the bottom. So if you haven't worked with things like that in a while, just make sure you're up to speed with how to juggle your logarithms and exponents properly. A word about this temperature dependence and just how strong it is. Okay, there's a rule of thumb that chemists use. I may have said this before, right? That says that for a lot of chemical reactions near room temperature, if you raise the temperature by 10 degrees C, that the reaction rate will actually roughly double. Okay, that's not exactly true for all reactions, but it's a ballpark guess that we sometimes use. Okay, I made an example here where I just ran some numbers. So I picked 100 kilojoules per mole for the activation energy, because that's a fairly typical ballpark order of magnitude guess. I picked 10 to the 13th per second for the pre-exponential factor A. That's also a relatively typical magnitude of that for a first order reaction. Okay, and we're not going to talk in detail about those because they're not all that interesting for us. And what I did then is I calculated the half-life of that reaction at some different temperatures. 100 Kelvin is cold, no doubt about that, right? But it's not unreachably cold. Liquid nitrogen boils at 77 Kelvin, right? And so if we wanted to, we could cool stuff off to 100 Kelvin. If we do that, basically, we stop our reaction dead, right? The half-life is 10 to the 39th seconds, which is in ordinary speak kind of forever. Okay, there are 86,400 seconds in a day, so that's roughly 10 to the 5th. So that number is something like 10 to the 34th days, which is, again, pretty much forever. So no reaction happening there, basically. Go up to 300 Kelvin, sort of a little bit higher than room temperature. That'd be a very warm room. But then the half-life has dropped down to be about 20,000 seconds. Okay, so 20,000 seconds based on that 86,400 seconds per day number, that makes 20,000 seconds, what, about 6 hours, give or take. Okay, so now we've got, over the course of a day, we could react a lot of this stuff, like more than half of it, right? We'd be through 4 half-lives roughly in a day. And so we'd have reduced the amount of stuff by 2 to the 4th power. Go up to 500 Kelvin, which would be essentially just kind of like putting something in a reasonably hot oven. At that point, my half-life will drop down to being 2 milliseconds. Okay, so by changing the temperature, admittedly, we went, 400 degrees is a fairly big temperature change, but in doing that, we've changed the rate of the reaction by 10 to the 42nd power or thereabouts. Okay, that's an enormous change. That has a lot of ramifications. The fact that rates change so dramatically when you change temperature is why a lot of things are done the way they are, right? It's why a good oven in a kitchen is calibrated so that it really does hold the set point temperature pretty closely, right? If your oven temperature wanders around and is at some points a few degrees too high, a few degrees too cool, then your cooking times are going to come out really erratic, and you're not going to be consistently able to make things that turn out well. Okay. People in chemical plants spend a lot of time and energy on temperature control because you don't want your reaction rate to get way off from what you're expecting, or any number of bad side effects could happen from that. The other place I always talk about this is just chemical reactions in your body. One of the major reasons why you just feel really rotten if your body temperature gets off by, even like 2 or 3 or 4 degrees Fahrenheit, which is not very much. That's enough to make you start to feel really bad, right? And that's just because various processes are no longer happening at the rates they're supposed to be, and some of them are getting out of whack with others, and that leads to a lot of the ill effects that you feel if you have a fever. Okay, so temperature control is a big thing in dealing with chemical reactions. The fact the rate constant changes so much, that's why in most of the kinetics problems, it'll always say this reaction was studied at this temperature, right? Students get frustrated by the fact that it says that, and then you don't have to actually use that temperature in the problem, right? It usually says that because the actual value you get for the rate constant would be different if you had done the experiment at a different temperature. But that's kind of why that's going on. So we know how to get a value for this activation energy now, right? So let's talk a little bit about just what it means. The other phrase people use instead of activation energy is often activation barrier. And it's essentially like the magnitude of this energy is telling us the size of the hurdle that the molecules have to climb over in order to get from the reactants to the products. Okay, the higher that barrier is, the higher that obstacle is, the slower the reaction will go. So let's take a look at this visually. This is a plot. When we started talking about thermo, I put up this plot and I said we didn't have to think about the part in the middle just then. We talked about just the fact that we could look at the reactants and the products, right? So for this reaction, my delta E looks like it's negative because I went downhill in energy from reactants to products, right? Now, if I look at the middle, this arrow up there, the E sub A, that's the magnitude of the activation energy, okay? On the top, I put a label up there, which I didn't really need to, but says at the top of the mountain, we have something that we refer to often as the activated complex, or sometimes the transition state. That's sort of like the point of no return. That's the maximum on this energy plot. If you go past that point, then it's downhill the rest of the way, and you're going over to the product side, okay? So in this case, my activation energy says that to go through this reaction, a molecule has to be able to climb its way from here up to the top and then roll down to be the products, okay? If that activation energy were to be smaller, that means the reaction would get faster because it would be less of an obstacle to get from the reactant side to the product side, okay? And that's how this actually works, right? In this plot, again, the x-axis is labeled as reaction coordinate. That's a somewhat nebulous variable or idea that refers to just where we are along the timeline of the reaction, okay? We don't get too specific about that. In many reactions, that would have a lot of actual physical and geometric values like all rolled into it. If it was a simple reaction where I was, just having two atoms come together and form a bond, then that coordinate would we could express that as just being the distance between the atoms, right? But if it was a more complicated reaction, then some bonds would be being made, they'd be coming together, other bonds would be being broken and coming apart. There'd be a really complicated array of physical quantities that would be rolled into that. So we usually just call that the reaction coordinate, or the extent of reaction is another phrase people will use for that. But that tells us what an activation energy is. So this, the graph that's there is actually a graph we looked at quite a while back. We're talking about gases. It's molecular speeds, okay? The speeds in there, I think, are for CO2 at different temperatures, but it's not too important what molecule it is, right? How does this activation barrier, how does it actually slow down or speed up the reaction depending on its size? The idea is that in order to react, the minimum thing the two molecules are going to have to do is they're going to have to collide. They're going to have to bump into each other. They can't actually react if they're far apart, right? I can't have a molecule over here and have it just like toss an atom through space to another molecule and change the composition. That won't work, okay? So the activation energy represents the minimum amount of energy that they have to hit each other with in order to be able to carry out the reaction. In a lot of cases, in the rate determining step, maybe the first thing that has to happen is we have to break a bond, just be able to snap an atom off of something to get another reactive species, right? You can imagine that the more energetically, the faster the molecules are moving when they crash into each other, the more likely they are to break something into pieces, okay? If I look at this says, suppose the energy it takes to be able to do a particular reaction corresponds to having this molecule move at 1,000 meters per second out there, okay? In the red plot, if I'm at 300 Kelvin, I have almost no molecules moving that fast. So my reaction will be very slow. In the blue plot, I have a fairly lot of molecules moving that fast, right? Because I have whatever fraction of the area under the curve is out there. So that's a decent slice of them, right? So my reaction should be much faster at 1000 Kelvin. The green plot for 500 would be in between, right? Because it's got, I already shaded on it, but it's got a little bit of area under there, right? More than the red one, certainly, but definitely less than the blue one. So the piece that's in that equation, e to the minus e sub a over rt, what that actually does is it calculates the fraction of all the collisions that have a relative energy, like an impact energy that is greater than e sub a, right? In another course that I sometimes teach, Chem 322, we talk in some detail about how to calculate that that's true and stuff. It just involves doing a lot of kinematics, basically just treating the molecules like hard spheres and figuring out their speed of approach and things like that. And it's possible to derive that form of that expression should work out. Okay, like a lot of things, that's sort of after the fact. When Arrhenius wrote down the Arrhenius equation in the first place, it was just based on empirical observations, measuring the rates of different reactions and saying, if I make this graph log of the rate constant versus 1 over t for all these reactions, it always comes out to be a line. Okay, and then later on, people put together some ideas, do some physics calculations, and make sense of why that equation actually works. Okay, so that was just an opportunity to bring back something from a long time ago, our speeds of gases, and say that ties in with the speed of chemical reactions, because it's the fact that the molecules are much more energetic that makes them more likely to react at higher temperatures.